Welcome to qnawire.
So here in this problem we have to find the speed of effusion of vapor from the kettle, and we are given that the area of kettle is 2 centimeter square, and the process occurs at the atmospheric pressure. So atmospheric pressure, we know it is 1.013 into 10 to the power 5 Pascal, or you could say Newton per meter square, and the power supplied is 1 kilowatt. So if we convert 1 kilowatt into watt, we'll get 1000 watt. And if we convert this thing into meters, so we'll get 2 into 10 to the power minus 4 meter square. Now we have to calculate the speed of effusion. For that, first we'll be calculating the heat. So heat in this case will be equals to the latent heat of a vaporization times the mass, where m is the mass vaporized or the mass leaving from kettle. And now the power, if first of all let us calculate the rate of change of heat. So rate of change of heat dq by dt will be equals to d by dt of, this is L of LV times m. Since the latent heat of vaporization is constant, so we can take outside the differentiation. So latent heat of vaporization times dm by dt. So this is the formula that comes out to be for dq by dt. Now if we calculate the power, the formula for power is nothing but the rate of change of heat. That means dq by dt. This is for power. Now if we compare this equation and this one, we can say that P is equals to LV dm by dt. From here we get dm by dt as power divided by its latent heat of vaporization. So this is the one formula that we have obtained. Now I'll be using the ideal gas equation. So we know that the ideal gas equation is P naught V is equals to nRT, where n is the number of mole and n is equals to mass divided by molar mass. So it will be equals to P naught V is equals to m divided by m RT. Now if you calculate the rate of change of volume, it will be P naught V divided by dt, and here also we have to take dt. So m divided by dt times RT by m. Sorry, it's capital M. M is the molar mass. Now if you compare this equation and this equation, dm and m, it's one and the same thing. So this equation becomes P naught V divided by dt is equals to, it's P divided by LV times RT divided by m. And we know that dv, if you consider this expression, this term, that V divided by dt, which is nothing but the rate of change of volume, and volume we know it is area into velocity. Rate of change of volume is area into velocity. So let me write velocity in this way. This will represent the velocity. So this equation becomes P naught A into velocity is equals to PRT divided by LV times m. From here velocity will be equals to PRT divided by LV, it's m, and P naught times area. Now we can substitute all the value here to calculate the velocity. So velocity will be equals to, P here is power, and power we are given as 1000 watt, that means joule per second, times R is the universal gas constant whose value is 8.314 joule per Kelvin mole, times the temperature we are given as 373, because it's a vapor at 100 degrees Celsius. So if we convert 100 degrees Celsius into Kelvin, we'll get 373 Kelvin. divide by latent heat. We are given as, we know that the latent heat for vaporization is 2.26 into 10 to the power 5 joule per kg. And the molar mass is 18 gram for water. But if we convert into kg, we'll get 0.018 kg per mole. And the pressure, we know it is 1.013 into 10 to the power 5 Pascal. And finally its area. So area is 2 into 10 to the power 4 meter square. So we're going to simplify and we'll get the velocity as 3.76 meter per second. So this is the final answer for the given problem.